Well, welcome to the SETI Colloquium Series. I'm Edna DeVore. I'm the Director of Education at the SETI Institute. And when I'm not here listening to all the great presentations and doing other things, I head up a program with the Girl Scouts. We're making a series of 6 new space science badges for Girl Scouts of all ages, along with sponsoring solar eclipse destinations next summer and several other kinds of things. It's really a very exciting project, and it's funded by NASA. So NASA's trying to engage more girls in STEM. But that's not my job today, to brag about my project. My job today is to brag about Gerry Harp. He's a longtime SETI Institute employee. He came to us in the year 2000, so this is going on 16 years, which is terrific. Gerry was trained as a quantum mechanic, and I can't remember that old joke about quantum mechanics eat steak, but I don't know if Gerry does or not. He may be a vegetarian for all I know. He got his PhD at the University of Wisconsin-Milwaukee in 1991 and spent the first half of his career working in experimental materials physics. Gerry and his group did basic research in the development of nanomaterials and special magnetic properties. And some of those materials are commonly used in computer storage devices that are available today. So he had one hand in the field of high-tech technology development for the first half of his career. In 2000, he joined the SETI Institute, drawn by the project of building what eventually became the Allen Telescope Array, a radio telescope that is still being used 12 hours a day, every day, in the search for extraterrestrial intelligence. Does everybody know where the Allen Telescope Array is? Lots of hands go up. Well, for those who don't, it's north of Lassen National Park, and it's a beautiful area. And if you go to Lassen National Park, you can actually visit the array and see the 42 telescopes out on the landscape. It's a fun thing to do. The ATA was a watershed of new technologies, and Gerry's research finds new ways to use the special properties of the Allen Telescope Array to improve our SETI search. In recognition for those contributions, Gerry was named, quote, the person most deserving of being burned at the stake in 2012. This incredible award is given by the SETI League and is also known as the Giordano Bruno Award. And it's named in memory of the philosopher-scientist that, just before Galileo was condemned by the Catholic Church, was indeed burnt at the stake for propounding ideas similar to Galileo's. One of his ideas was that there could be civilizations around other stars. So this is not a new idea, but it's not an idea that's been proven. And Gerry's here to talk to you today about our SETI research and how we are continuing to look for those civilizations around distant stars. I bring you Gerry Harp.
Thanks, Edna, and thank the organizers for asking me to come. It's really a pleasure to talk to you today, and I hope that I can present some ideas that are a little bit novel, because I think you've all seen multiple SETI talks by now, and so I don't want to repeat things that have always been said before. So I really like this picture. It's pixelated on this particular display, but because it looked very realistic on your computer. And if you wonder where this picture came from, then you're going to have to wait. Okay. So basically, if you Google faking a UFO in Photoshop, there was a contest for that, of course, and you can get a lot of cool pictures like that. Okay. So I'm going to talk a little bit about what we know about ET, which you would think is not very much, but there are some things that we can say about ET, even without having discovered them. A little about Fermi's paradox and what that says about us, and how ET might communicate across the galaxy, and then briefly talk about the exoplanet search that we recently just completed, and a power beam search, which is a new way of looking for SETI signals from stars. So what do we know about aliens? Well, if you ask Hollywood, you know that they have big heads and 2 eyes, usually big eyes. And turns out eyes might not be such a bad idea, because eyes have developed on Earth through independent evolutionary paths twice. at least twice. Octopus have eyes, and they're not at all genetically related to our eyes. So eyes are actually pretty useful to have, and if they develop twice, maybe they develop elsewhere. However, having them... Oh, thanks. All right. So if you go to Japan, you'll see different kinds of images, and this is because back when War of the Worlds came out in Japan, it was accompanied by pictures like the one at the top there in yellow, and people thought that that looked like a squid. And so now in Japanese movies and cartoons, you'll see a lot of squid-like animals. But what else could there be? Well, there's parasitic aliens, and then there's, of course, extremely scary aliens. And so this is what movies would tell us, but of course that's all hogwash, except maybe the eyes. So what can we tell about SETI, or ET rather, that we don't already know? Well, they're probably older than us, and this is a very simple argument. The Earth has been around for 4.5 billion years, and we have been sending signals technologically that could go through space for only about 100 years. So the fraction of time that we have been able to communicate with other stars is so small compared to the fraction of time that the universe has been around. It seems very unlikely that we would just happen to find another civilization that's exactly the same point in their technological development as us. And chances are they've had technology for longer, and probably they have better technology than we do. So this is just me now, but in my opinion, they're probably carbon-based if they are biological life forms. And this is kind of interesting, because if you look at the chemistry of carbon, you'll see that it can make 4 bonds, and it likes to be in a tetrahedral arrangement. So in a minute, I'm going to talk about nitrogen and oxygen, but just point out that nitrogen here and oxygen only allow fewer bonds. But another thing is that carbon, because it's such a small atom, is very flexible in the way that it can bond to other atoms. So here we have double bonds, and you can see how these tetrahedral bonds are now distorted quite dramatically. And you can also have like acetylene here, where you have triple bonds. You can have aromatic bonds, like in benzene. So all of these different possibilities are available as building blocks for life on Earth. And so I would argue that if you compare that to something like a silicon-based life form, now silicon is right under carbon in the periodic table. It also makes 4 bonds, and it also likes to be tetrahedral. But silicon is very stiff. It's not flexible. So even though you can make something like benzene with silicon, it doesn't flatten out in a plane real nice. It's actually not a very flexible molecule. So I would say that in any evolutionary competition between silicon-based life and carbon-based life, probably carbon is going to win, also because it's a smaller atom. Chemical reactions sometimes happen faster than they would with something like silicon. Also, we're made out of the most common elements in the universe. Human biology, excepting helium, which is a noble gas, is mostly based on the 5 most common elements in the universe, right? So we're just made about whatever happened to be lying around whenever we started, and that's going to be true other places as well. So a lot of people worry about the aliens coming and eating us. I don't think that's going to be true for a number of reasons. First of all, there's a lot of things on Earth that are alive that we can't eat. We can't digest cellulose. And so the chances that they would come here and find us to be easily digestible, it doesn't seem very high to me. And furthermore, our digestive requirements are very strict. There's a thing called chirality, where you can have 2 molecules that are identical except they're mirror images of each other. And for example, this isn't showing sugar, but it could be a sugar, right, like table sugar. And if it's left-handed table sugar, you can eat it, and it tastes delicious, and you can gain a lot of energy from that. If it's right-handed sugar, you can eat it, and it tastes delicious, but your body can't digest it, and it just goes right through you. You gain no energy from it. So if you were on a diet of right-handed based sugar, you would starve to death. So that's another reason that we are probably not going to look very tasty to the aliens. And finally, wouldn't they just grow their own food that they already like? You know, they can use the sun as a better energy source than the Earth, you know, because the sun produces a lot of energy and there's only a little bit of energy that's caught by the Earth from the sun. So if you really want to go for the big energy source, why not just go for the star? Now I'm going to say that they are probably not here, and I don't think I have to convince you that there's never been any substantiated evidence that there are aliens around on the Earth. But people like to see UFOs in the sky lots, and this sort of cracks me up because this image, take a look at it, is the best UFO sighting of 2013. So if that's the best image that they have of the UFOs, it's not very convincing. And this is a restaurant. So the Fermi's paradox is an idea that came up by Fermi, obviously, and it's a way of thinking that actually is sort of a strong argument against there being any other intelligent species in the universe or civilization. So basically, Fermi was sitting around with his buddies at lunchtime, and they had been having a conversation about how many suns in the galaxy might actually have civilizations around them. And everybody was saying, well, it seems like there would be a lot. But then Fermi said, well, where are they? And what he meant by that is that there's all these billions of planets and millions of intelligent species. How come they haven't visited us? Right? And so that's a pretty interesting argument. But I'm not going to argue with you about Fermi's paradox. There are whole books written about Fermi's paradox. I just want to point out one thing about Fermi's paradox that says something about us. And that Fermi's paradox contains a hidden assumption. That which is not forbidden is compulsory. And to put it another way, if the aliens could come here, they would. That's the assumption. Right? So, and this phrase was coined by T.H. White in The Once and Future King. And it's got its origin in the English Constitution, which is also, it's a very important statement that is also true in the American Constitution, that everything which is not forbidden is allowed. So if you come up to somebody and you see them doing something strange and you say, hey, should you really be doing that? They can tell you, well, there's no law against it. And you have to shut up because that's the way our law system works. But that's not true everywhere in the world. And in sort of a tongue-in-cheek, you can summarize the law systems of other parts of the world as follows. In Germany, everything which is not allowed is forbidden. In France, everything is allowed even if it is forbidden. And in Russia, everything is forbidden even if it is allowed. So, although this came from a fiction novel, Murray Gell-Mann, who is a famous particle physicist in the 60s and 70s, sort of applied this concept to particle physics. And the idea there is that nature cannot do anything that is forbidden by a small number of physical laws. And we know we can enumerate those laws, and anything that is forbidden by the laws will never appear anywhere in the universe. On the other hand, anything that is not forbidden by those laws is always seen. And this is true in physics. It's sort of a law. There's no reason to, you can't prove that this is always the case. But in fact, whenever we go looking for stuff, looking for new particles, if there's a way that a particle exists having certain properties and stuff like that, we go look for it and we find it. And if it's not found, then there must be something wrong. So, for example, all massive particles, baryons, are known to decay. And this is radioactive decay, where the large massive particle breaks up into a bunch of smaller particles. And so no matter what kind of particle you start with, it's going to decay and decay and decay and decay until eventually you get protons. Now, protons are also massive particles, and there's good theoretical reasons for thinking that protons should also decay. And so that's kind of a mystery. Why don't protons decay? And a lot of people think that protons actually do decay. It's just that they last a very, very long time before they decay. And so the universe hasn't been around long enough for us to notice that event. But anyway, this is a powerful tool in physics, to sort of approach problems where you don't have any structure at all, and you just sort of say, well, where do I start? So Mary Gellmann is also famous for saying, if I have seen further than others, it is because I am surrounded by dwarves. So here's my point. What does Fermi's paradox say about human behavior? Basically, it says we sort of assume that if aliens could visit us, they would. And that comes from human behavior, which is basically anything that can be done will be done eventually. And just think about it. All of the amazing, terrible, and wonderful things that humans do, and you read about it in the paper every day, and you think, gee, I would never have imagined that that could possibly happen. But humans explore all possibilities. And so this is an anthropomorphic concept that we project onto aliens, assuming that they would do the same thing. So for example, humans have made thermonuclear bombs. Not sure if that was a good idea. Humans invented teenage hairstyles and weird Japanese inventions. I love this because you can sleep on the train on the way home. But also, we can use this same principle, speaking of humans, to predict the future. So for example, anything that you can think of that seems reasonably possible with technological means is going to happen. And so the first of that might be giant robots. Yes, there will be giant robots. I predict that with a lot of confidence, because there can. And similarly, there will be chimera, because in fact, you've heard on the news probably that they're already creating chimera. So, and not so clear that that's something we should be doing, but we're doing it. We're human. The last thing is time machines. Well, if there were a time machine in the future that could come back to the present day in time, we would know about it. So I can say with confidence that in the future, there will never be invented a time machine that can come back to this day and time. Right? So it's just a corollary of that principle. And finally, active SETI. Now, I'm not going to talk about active SETI, but you may have heard of it. It's the idea that instead of just listening for signals that are coming from outer space, we transmit signals to outer space to try to get the attention of ET. And the idea there is that if we get their attention, they can probably teach us a lot. They may be able to save us from ourselves. There's a lot of good benefits that might be caused by that. But there's a lot of people who think that's a bad idea, because they say, well, if you attract their attention, they're going to come here and eat us, or raise the earth. So you can argue about that, but the point is that humans are going to do it. In fact, they just recently did do it. I think you heard of the ESO maybe, who recently sent a strong radio signal toward Polaris. And so even though there's a lot of people in the world who might object to this happening, it's happening. So now this is a very dense slide, and I'll just go through it one line at a time. But it's this Murray-Gell-Mann approach to the SETI problem. So what we do is we start from the beginning. We start with the physical laws, and we say, what is allowed by physical laws? And then there's sort of another step where we say, what is allowed by our own technology? And then anything that's left over is a good way to look for communication signals. So for example, as far as we know, all communication requires some energy to be exchanged between two places. And there's many ways that energy can go, like first of all, gravity waves. Gravity waves are great because you can't shield gravity waves from anything. They go through everything. And so you would think this would be a great way to communicate, and it probably is. Unfortunately, our detectors are not that good. I mean, we can just barely see two black holes colliding with each other with our gravity wave detectors. So unless ET is sending one bit by collapsing black holes one after the other, we're probably not going to find that right now. Doesn't mean that we won't in the future, but it's not feasible for us. And then there's the electromagnetic force, which makes electromagnetic waves. So that's light, or radio waves, or photons, if you prefer. And so that seems like a good idea. It's a very long-range force, so the light propagates long distances, and we know how to detect it reasonably well. So that seems like a good idea for SETI. Now, then there's the strong force, just going through all the forces in the, of nature. Strong force is a nuclear force. It holds the nucleons together, the atoms and the protons together in the nucleus of an atom. And it's a very short-range force. It doesn't go beyond a range that is much smaller than the size of an atom. So think of an atom, that's pretty small, right? The strong force only acts over distances smaller than that. So using this to transmit signals across the galaxy doesn't seem reasonable because it decays too quickly. The same is true for the weak force. Now, the weak force is what causes radioactive decay in the nucleus. And once again, it's a short-range force, so that doesn't seem like a way that we can communicate. And then there's dark energy, the fifth force. Now, we don't really know for sure that this is a fifth force, but a lot of people think that it is. And if dark energy is the fifth force, then we can probably make dark energy waves and could transmit things very long distances between galaxies with dark energy waves. Unfortunately, we don't even know what dark energy is, and so we can't really measure it, so that's not what we do. Lastly, and this is supposed to be an exhaustive list, but you can tell me if I'm missing something, is matter. One way to communicate with another person is just write something down on a piece of paper and hand it to them. So, or you can use elementary particles. And elementary particles are nice because if they're stable, then they're sort of unchanging. Protons and electrons are good choices, except for the fact that they're charged. So in the galaxy, there's lots of magnetic fields around, and if you try to push a charge through a magnetic field, its path will just be diverted, and it will never arrive at its destination. So turns out those are not so great for communication as far as we know. But then there's neutrinos, which are neutral elementary particles. And neutrinos are a very good idea. Once again, these things, they're very, very small, they're very, very low energy, and they pass through just about everything, right? Except maybe the center of a star. So if you want to make communications with neutrinos, that's a great idea, except that they also pass through our detectors. Our neutrino detectors are things like 1,000 tons of deuterium water just to detect a few neutrino events, right? So these are really, really big. And so although we should look at this data just to see in case there's something interesting in the data, there isn't a lot of data to look at. So that's not what we do. And finally, solid objects. You can hand somebody a piece of paper or a disk drive. And the way that you might do that is by creating a space probe and sending it to our solar system. And this is a very good idea. And in fact, we are doing SETI this way right now because there's a lot of people studying asteroids and getting up and close to them and looking at them carefully. And if one of those turned out to be a space probe, we would find out. So there's really only two ways that we can think of that it's sort of easy to do SETI. It's with electromagnetic waves or by exchanging objects. So you've seen this before. I'm not going to talk anymore about solid objects, but electromagnetic communication. There's really only two places in the electromagnetic spectrum where our atmosphere is transparent. And why does that matter? Because our biggest telescopes are on Earth for obvious reasons. It's a lot easier to build a big telescope on Earth. And so anything that we look at has to pass through the atmosphere. And the atmosphere really has, at most frequencies, the atmosphere will absorb all this radiation, except in the optical range and in the radio range, and I'll blow that up. So here's what the radio frequency range looks like. So here we have between 1 and 10 gigahertz, we call it the terrestrial microwave window. And what this is showing here is the absorptivity of the atmosphere and everything else, coupled with the background radiation. So it turns out that if you move up into the infrared frequency range, our atmosphere absorbs all that infrared radiation, mostly at these low frequencies through rotational transitions. And And so you have to go below the lowest rotational transmission in order to get something that will pass through the atmosphere. But at the same time, the galaxy has a lot of background radiation at lower frequencies. And so even though you could use that to communicate, you would have to make your signals a lot stronger to overcome the background noise. So we think that this is a pretty good range to be looking, between 1 and 10 gigahertz. Now, there's something interesting about this, is that all rotational, no matter what kind of a small atom you have, or a large atom for that matter, the rotational transitions happen at roughly the same energies. So even if ET is on a different planet and they have a completely different kind of atmosphere than we do, very likely they can't transmit from the surface of their planet in the infrared, because it will also be absorbed, maybe not by those atoms, but by other ones, molecules. Yeah. So next, what do we look for in SETI? And so basically, SETI is we look for things that we think can't happen in nature. And why is that? Why should we eliminate things that could happen in nature? Well, simply because if we find something that could happen in nature, it's very difficult to prove that it didn't happen in nature. And so what we do is we look for signals that, as far as we know, can't happen in nature. And we create what we call frequency spectra. So here's one. So just imagine any one of these lines. And the line has 3 bumps on it, mainly. And these narrow bumps, so we have frequency on this axis, or that is color of the radio frequencies. And on this axis, we have time. And so what we see is 3 strong signals in all of these lines across the sky. And then what we do is we look back again and again and again at the same object to see if those lines are consistent. Oops. If they're always the same, or if they change in amplitude over time, or something like this. And so what we construct here is what we call a waterfall plot. And I'm going to be showing you some waterfall plots, which are basically a grayscale version of an image like this. So here's an example. This is one of our waterfall plots. So we have frequency across the bottom, and time across the top, across the vertical. And let's see if I can make this happen. So there's a signal embedded in this signal, which just popped up to show you, but oh darn. Well, it's not going to show you, but if you look very carefully, right here you can sort of see a really, really weak signal, which is from the Voyager spacecraft. And if we integrate over the whole waterfall, then we can get a spectrum like this to prove that this is really a strong signal, and it's an unnatural signal. It has to be artificial. We know it is because it's a spacecraft. These are more waterfalls. This is sort of like the everyday meat and potatoes of SETI. So that we have all these waterfall plots, and we see all kinds of different things, and we don't really know what they are. But they all appear to be artificial because they're all fairly narrow bandwidth. So in these plots that I'm showing you here, the frequency bandwidth on the bottom axis is about 500 hertz. And that just so happens to be that in nature, the narrowest frequency spectral lines that are seen in the microwave range are about 500 hertz wide. So anything greater than 500 hertz in width is not artificial, but we look for things that are smaller than that. And we see things like noise. Well, this is what we mostly see. And then this is what we call a candidate, because this is the kind of signal we think if ET were sending us a beacon that it would look like. And then there's other things, zero drift RFI, which sort of are vertical in this image. There's also radio frequency interference that appears horizontally along these images. And we think that those are almost certainly earthbound, Earth-created signals, particularly this one, because what it's saying is that the transmitter and our telescope are moving with each other exactly together. And if they're moving exactly together, it's very difficult to imagine that ET knows exactly where we are and the motion of the Earth and the rotation of the Earth and where the telescope is on the surface of the Earth that would be required in order to make a straight line plot like this. So anything like this, we can be pretty confident it was made by humans. And then we have what we call squiggles, which is an interesting class of signals. I mean, we can speculate on where they come from, but they are artificial looking, and we don't have any sure way of knowing whether the squiggle signals are, pardon me, whether those squiggle signals are coming from outer space or not. I'm just looking at the signal, you can't tell. So I'm going to tell you that in the research that I'm talking about today, we're going to be talking about candidates that look like this. But these signals we're going to leave behind, simply because our instruments aren't good at detecting things that sort of change in frequency in sort of a random way over time. And we hope in the future to build detectors that can detect such signals, but not today. So what do? We build a big radio telescope. This is what attracted me to the project, because the ATA was a really interesting new project where they were going to try to build a large radio telescope for a very small amount of money. And so instead of just building one great big dish, what you build is a lot of little dishes, which are a lot cheaper. And then you combine the signals from all those dishes together, and you make effectively images of the sky. You can take snapshots. This is a snapshot camera, and in the radio frequency range. And so this was, it was not entirely new, but a telescope with this many dishes and this small dishes was brand new. And I keep saying that they're small dishes, but really they're 20 feet in diameter. So if you think that's like 2 stories tall. So from a human perspective, they're actually pretty big. But from radio astronomy perspective, they're not so big. And here I was talking about the frequency range. This is the very frequency range. They were designed, in fact, for the SETI search. And so they cover all the frequencies in the radio where we think we might find SETI signals. That's a great thing. And it has also some properties that make it really good for seeing large parts of the sky at the same time, so that we can search effectively for SETI, for ET. And it's dedicated 12 hours a day, every day, as we speak. Well, not probably about 7 o'clock in the evening tonight, it'll start observing again. So this is ongoing research, and we could find the signal any day. But what's our biggest challenge? You wouldn't think so, but the biggest challenge in radio astronomy, and all kinds of radio astronomy really, is what you would call lens flare. And most of you know what lens flare is from optical photography. So basically, there's some very, very strong source out here, which is so strong that even though the camera isn't pointed at it, the light rattles around in the lens of the camera and eventually hits the detector, the CCD on the camera, and creates what I'd like to call non-imaging energy or intensity in the image. Anybody? What is the signal that's strong here? The sun, obviously, yeah. The sun is also bright in the radio frequency range, but there's much worse things, which I'll talk about in a minute. So just zooming in on this little place about the flare, you see, compared to the image in the background, you get this sort of hazy structure that sort of fills the whole image. That's lens flare. You get these streaks, which again, the streaks, this, it looks a little like a tree, but not really. And you see these blobs from the sun. And so just by categorizing these on the basis of their shape, we can know something about where that light is coming from. And that's how we overcome lens flare in radio astronomy. So as I was saying, the worst things of all are satellites in the sky, because you can't hide from a satellite, especially the geostationary satellites. And they're very, very strong compared to anything that's coming from outside of the, elsewhere in the galaxy. So these are effectively suns for our system, and non-imaging light comes into the dish and rattles around and gets into our receiver. The ATA is built in a kind of an interesting way. It's an offset design. So although it looks like it's sort of pointing up here, it's actually pointing straight up. And so basically, you go from the center of the big dish to the bottom of the big dish to the top of the secondary dish, and that's the direction it's looking. So this antenna is looking straight up, but there's light coming in from the side that is polluting the images. So what does that look like? Here's a radio image of a quasar, which is a very large exploding galaxy, a billion or so light years away. And so when we image this with our telescope, it's a very bright thing. It just looks like a point. It's like a star. And so our images are relatively low resolution compared to what you're used to with optical telescopes. But this is a point source on a black background. And that's just the kind of thing that you would expect to see if you're looking at the region around a star in the sky, or a galaxy in that case. But here, this is exactly the same time this data were taken, and exactly the same, just a different frequency, where exactly the same data, and you see that there's a lot of non-imaging intensity in that image. So this is RFI. So now we have a test. You can easily build a machine that can look at these two images and say, hey, this one looks real, this one looks like garbage. And so you don't actually have humans doing all of that work. And that's the basic principle of how we search for SETI signals, how we eliminate all the Earth man-made signals that get in our way. Now, although we would really like to make complete images like this, to do it fast enough for all the different frequencies that we want to do in a SETI search is sort of beyond our technical capabilities right now. So what we do is that we just take 3 pixels from this image. So this is the size of a pixel, if you will, or a beam. And so we have 3 pixels put in different places in the image. And then by comparing the signals in those pixels, if they contain the same frequency, those 2 pixels, then it must be coming from something that's sort of splattered all over the image. But if all the pixels are independent and none of them have that signal that you see in one of them, then it's more likely looking like this, which is about what we would expect a picture of an ET beacon to look like. So this is the principle behind our methods. How big of a challenge is RFI? It's really, really big, and it's getting a lot worse with time. So back in 1995, at the top, you can see the Parkes Radio Telescope. So we have frequency on the horizontal axis. And what we put is bars where there's so much interference coming from human beings that we can't ever make any decent images of the sky. These bands are just so polluted with interference that we can't look at them at all. And so in 1995, there were a few of those bands. And then in 1998, at Green Bank, there was more, right? And then in 2004, at Arecibo, there was a lot more. And then in 2006 at the ATA, this is the band. So now the ATA doesn't just look from 1.2 to 3, it goes all the way from 1 to 10. So this graph is longer, but you can see now there's already a big block right here, which are the satellite TVs, TV satellites, which completely cover this range. And then even more recently, this is 2015, and I just comparing the two, that you can see that the RFI continues to grow. So in a way, doing Earth-based SETI observations is, we're looking through a window that's rapidly closing in time. And so you ask, well, shouldn't we wait until we have better technology to do this? Sure, but if you do that, then you're going to have to go out into space. And building telescopes in space is a lot more difficult. So this is one reason why we should feel a sense of urgency about doing the SETI observations now. So now I'm going to give you some results of, it says greater than 3 years of observations. This is about 6 years of observations. And I'll give you a little background. So these observations were done on stars where we believe there are exoplanets around those stars. And so exoplanets have only been around, people have only known their existence for about 20 years. And nowadays, there's roughly a few thousand stars where we're pretty confident that there is a planet around that star. And so the idea is that, assuming that exoplanets are rare, why not just look at those stars that have the planets? Because those would be the most likely to be inhabited, right? If there's no planet, where would they live? At least that's the idea. And so that's why we started looking at exoplanets. But in a minute, well, I'll just finish with the conclusion. It turns out that the Kepler Space Telescope, which went looking for exoplanets and tried to quantify the probability that there is a planet around any star, it turns out that almost every star has an exoplanet. So indeed, just looking at the stars where we know there's exoplanets, there's really no advantage, because we can point at any star and there's probably planets there. So, for a period of 6 years, we thought it was a good idea to look at exoplanets only, especially, and it was an interesting problem. I mean, it's as good as anything else to look at. Oh wait, is that the wrong slide? Oh, I included the wrong slide. Well, I'm sorry. Basically, 6 years of observations, we found about several million signals. And these are signals that sort of passed our first stage of categorization. So that they're not already known to be RFI, and they don't have this zero drift property. So these are signals that are sort of candidates that maybe such a signal could be ET. And so 3 million over 6 years. And then over that time period, we use this direction of origin method. So basically, we use multiple pixels in this image, and we compare them. And if a signal ever appears in more than one of those pixels, we say that's got to be Earth-made interference. And using just that technique, or primarily that technique, we were to eliminate all of these signals and prove that they were all coming from Earth. And so far, we haven't found a signal that we could not prove it wasn't from Earth. So no ET so far. So sorry, yeah, well, just suffice it to say that it's a lot of work, and we're very proud of this work, and we republished it recently, so you can look at it in more detail. We're also trying new things with SETI, in radio SETI, and there's a new idea that sort of came out from, most popularized by the Breakthrough Starshot project. So Breakthrough Starshot is an idea that you take a very, very small microchip, which is maybe weighs less than a gram, and you attach an umbrella to it, facing backwards, and then you shine light into that umbrella and push the satellite forward. And because it's so light, you can use something like a bunch of lasers all coupled together in such a way so that they all aim at the same place in the sky. And so here's that beam coming up from the Earth, and here's the umbrella pointed backwards, and right here is the microchip. And so you can push this thing to speeds very close to the speed of light, and therefore you have a starship. So there's a lot of reasons why this is a really good idea for propelling a spacecraft. For one thing, you don't have to bring the fuel along with you, and that's one of the big problems with rockets. The fuel is very heavy, and so you expend the fuel, and it turns out that almost all the fuel is wasted pushing the fuel up into the air. So this is efficient and also doable. So it wasn't long after people started thinking about these ideas that someone decided, well, hey, you could do this with microwaves just as well as light, because microwaves pass through the atmosphere too. So basically, what in the microwave frequency range where the atmosphere is transparent, what you might expect to see is like if you were looking at this from a long distance, you'd see a very, very, very bright source, and it wouldn't be extremely narrow band, because if you want to make a really powerful radio transmitter, you don't want to make it, you want it to sort of be sort of fat in terms of frequency space, because it's easier to build that way, it's cheaper. So you could say, well, maybe ET is using this microwave beams in order to push their spacecraft around, and maybe if we put our radio telescope at a planet or at ET, then we'll see those beams. These are not intended for communication, but they're actually intended for propulsion. And so there's some interesting papers. This one is by Benford and Benford, which show that there's different ways that you can use power beams. You can take it from the Earth into orbit. You can take it from one orbit to a higher orbit. You can take it from Earth to another planet. You can take it from Earth to a star that's going at 0.1 of the speed of light, or you can take it from Earth to a star going at 0.5 at the speed of light. So all of these things are possible, and with the right technology, you might be able to do it. So the question is now, if these are microwave beams, which ones could our telescope see, the ATA? And it turns out that if you sort of work out the numbers, the threshold for the ATA could see one of these beams if it had a power of about 10 to the 19 at, I think, 100 light years. So here, these are the powers that we required here. So to launch to orbit, 10 to the 19th, we could barely see that. Orbit raising, we probably can't see those. But interplanetary and interstellar beams, we could easily see those on the background, right? So our previous SETI detectors were not sensitive to these signals. Even though these signals might be extremely bright, we're always focused on just very narrow band signals. But if it's something this powerful, it's not going to be narrow band. And so we have to build a different kind of detector to look for it. And well, that's sort of what we decided to apply to it. Well, I'll talk about that detector in a minute. But at the same time, in 2015, Tabitha Boyajian discovered a very interesting exoplanet system, Tabby star, which is also known as KIC 846 2852, where using the Kepler's telescope, they noticed that this star was getting dim. Now, you expect the star to get dim if, for example, a planet goes in front of the star, it blocks some of the light, and so the star appears to dim in your telescope. But this dimming was way bigger than anything that has ever been seen before. And we're talking about 20% dimming sometimes. So if you think about how big a planet would have to be in order to block 20% of the light from a star, it has to be a pretty big planet. And it's so big, in fact, that it wouldn't really even be a planet anymore. It would probably be a brown dwarf. So maybe there's a brown dwarf orbiting this sky. But if there were, then you would see brown dwarfs tend to emit strongly in the infrared radio frequency range. And so they did infrared measurements, and they found out that there were no infrared excess. So it's not just some big object going in front of the star. It's got to be something else. And so Jason Wright, if you were here a few weeks ago, he was talking about this exact same thing. He was saying that maybe what we're seeing here is evidence of extraterrestrial civilization, that maybe they have built some sort of a very large structure around the star, like a Dyson ring or a Dyson sphere, that blocks the sunlight. And then as that object rotates before our telescope, the light gets dimmer and brighter. And this could block a substantial amount of light. So that's pretty speculative, but still, it's interesting. It looks like an interesting star to look at. And so we took this new technique that I was talking about, looking for power beams, and applied it to this star. And here's the result. So basically, it's very similar to the plots that I showed you earlier. It's a frequency spectrum. And here we're just showing the strength. We're showing the strength of the signal that we observed as a function of frequency. And here we're covering the entire 10 gigahertz bandwidth. So this is kind of an exhaustive search at some level. And you can see that there's a lot of things that look like peaks in here. And some of them even look like, sort of like what you might see for a power beam. But we went back and checked all of these peaks by making images, full-blown images around these peaks in that frequency range. And none of those images looked like a point source. They all looked like just splooge all across the image. So we can say that within the limits of the ATA to measure, we can be pretty confident that during the short time that we did observations, they didn't launch an interstellar ship in our direction. So it really doesn't say very much, but it is sort of demonstrating that we're trying to improve our, look for signals in different ways, and expand the search as we can. And that's what my research has been about, and it's something that's very exciting for me to do. So now I just want to say a couple of words about the future. I'm not going to give you a lot of detail, but basically, I said that our current system uses 3 pixels in the image. And if we had more pixels, then it would be an even more useful technique, because the chances of a signal showing up in, say, 1 of 8 beams, or 2 of 8 beams, is higher than a signal showing up in just 1 of 3 beams. So anyway, more beams is better. And the limit with the ATA, with our instrument, would be about 1,000 beams, or 1,000 pixels, independent pixels in our images. And this is where we want to go sometime. And so we estimated how quickly we could eliminate radio frequency interference if we had more and more beams in the system. So here, this is a single dish. You can't eliminate anything because you can only look at one direction at a time. With 3 beams, here we are at the ATA. Every time that you look back at that source, there's a 40% chance that it won't be there, or it will show up in 2 beams. And so we can eliminate it very quickly. If we had 8 beams, then you could improve that. So you could eliminate all of these signals up here in just 1 observation. And then you would need fewer observations to get to classify all the signals, and therefore you could search faster. And that's what we want to do. We want to search as much as we can of the sky. It's still a long way before we get the whole sky. So faster is better. And finally, as I was saying, if you could do all the beams in the radio telescope, we would get essentially 0 probability that a RFI signal would appear in only 1 of those beams. So this would be very, very effective, but it's also very expensive computationally. So it's something that we look forward to in the future, and maybe the people at Microsoft can help us get there. Okay, so just to conclude then, ET, we think, does have to obey the same laws of nature that we do, and therefore that allows us to say some things about ET, even though we don't have any information about them at the present time. Fermi's paradox says something interesting about people, that anything that you can think of, some person is going to do it eventually. And so then I talked a little bit about our radio observations. A couple of weeks ago, Elliot Gillum talked about optical observations. So we're doing multiple thrusts in order to find ET. And finally, there's nothing so far, and we keep improving our methods. And SETI research needs your support. So I encourage you to go to www.seti.org and learn more about our organization. Thanks.
Gerry will entertain some questions if you have one. I'll bring the microphone around because, as you know, we record these.
I had a comment and a question on your Fermi paradox. I thought you were going to go to the supposition that maybe they're smart enough they don't even care if we know they're there. And why would they even bother? Because it would be asymmetrical. The question the question I had was, we also have something called spread spectrum as a way to communicate around Earth. And is that becoming more and more of a pollution to background radiation, which will eventually drown out your system from 1 to 10 gigahertz?
Yes. Well, yes, spread spectrum is a problem, a growing problem for us. Fortunately, it tends to look a lot like Gaussian noise, or at least if it's done right. So it raises the noise floor, but it doesn't make it completely impossible for it to look in certain frequency ranges. Also, on the other side of that, why wouldn't ET be using spread spectrum signals to communicate across the galaxy? And we think that they might do that. And we're working on creating new detectors that are able to find those kinds of signals that we can run alongside our current detectors.
So I think recently our estimate of the number of galaxies in the universe went up by like 2 orders of magnitude does that affect your calculation in any way, and how does it affect Fermi's paradox?
Well, there's been a lot said about Fermi's paradox. If we count all the galaxies in the known universe, and all the stars in those galaxies, there's something like 10 to the 22 stars total. And so with such a large number and the presence of us already existing, you can argue that it seems unlikely that none of them are inhabited apart from our own. And Fermi's paradox says, well, why haven't they come here? Well, if they were in a different galaxy, it's rather hard to make that long journey. That's a much longer journey than it is from one side of the galaxy to the other. So that might be a reason why they haven't come. I mean, it would take billions of years, literally. So, the universe has only been around for 13 billion years. But yeah, there are some, like some people have suggested that quasars, which are these very, very bright exploded galaxies, are actually, could possibly be some kind of a way for ET to communicate between galaxies. Now, the idea is that if they had some sort of control over this process of the black hole in the center of the galaxy accumulating all this matter, if they could control that, then they could control the radiation that's being emitted and therefore embed information. And so if we look carefully at those quasars, we might see something in them. We did an experiment like that. It didn't show anything, but yeah, there's a lot of things you can say about Fermi's paradox.
So, Gerry, I was interested in your comments about the infrared and the atmospheres of other planetary bodies. Because, as you know, we've been suggesting that we ought to be pushing the current optical SETI searches down into the infrared to get greater reach because they won't be scattered by the dust in between the stars. But now you're suggesting that independent of the composition of the atmosphere of an exoplanet, transmitters through that atmosphere in the infrared aren't going to be very easy or likely or efficacious. So I'm trying to puzzle out whether we should be looking in the infrared or not.
Well, the infrared spectrum is actually a very broad region of frequency spectrum. And so if you go up to the part of the infrared that's just below optical, that light does get through the atmosphere relatively well. And by going to a lower frequency in terms of that light going into the infrared, as Jill says, less of that light is stopped but blocked by gas and other things on its way coming to us. So that would be a good way to communicate. But what I'm saying is more that at the very low end of the infrared range, where we do radio signals, anything above 10 gigahertz is likely to be a problem anywhere.
Back about slide 30, you had this plot, a frequency plot of the signals that you've found and explored, and there was a red line on there. Can you tell us what the red line showed?
Oh, yeah, so that was just an example of I'm sorry that I can't go back in the slides, but, oh, wait, there it goes. Was it 32? Okay. Right. Oh, yeah, so the red line, that's just a simulation of perhaps one kind of power beam that could be used. That's sort of on this order of the energy of the ones that we decided were reasonable for pushing spacecraft around.
Okay, back to elementary particles, considering candidates for communication. What about supersymmetry particles like the photino, the hypothetical supersymmetry of the photon?
Well, if they're long-lived particles, it's a great idea. And, then, there's only the technological problem of actually building a detector for those
But there
things.
might not be a lot of noise in photinos.
Right. That's a good idea. Actually, if you could make a communication device that used photinos on Earth, you'd be a very rich man.
One more question.
Maybe an even crazier idea for something left out of your list of communication. What about quantum entanglement communication? Could you comment on that? I mean, in principle, it's the only way where you could have a two-way conversation because it's instantaneous.
Well, there's a lot of confusion in the public press about quantum entanglement. Quantum entanglement can be used, for example, to hide information. So if you want to send a message from here to Russia and you don't want them to be able to open that message until tomorrow morning, quantum entanglement provides means that you could possibly do that. But to communicate within quantum entanglement, you have to have a classical route between the transmitter and the receiver. And so basically, I can use quantum entanglement to transmit some information, but there's no way to interpret that information unless I send a code book. And the code book has to go at the speed of light. So there is no way really of sending messages faster than the speed of light with quantum entanglement. And furthermore, if you don't have the code book, you're just really, you have no idea. There's no way that you can interpret what you see.
Well, I want to thank Gerry. Let's give him another hand. And just in case you haven't encountered one of these terrific SETI.org mugs, thank you very much. Yay. And I'd also like to reinforce what Gerry said at the end of his talk. Our SETI research is all privately funded, and I would invite you to be part of the group that helps us to continue that search. It's not funded by the government. So thank you very much. You're welcome to come up and ask Gerry any individual questions that you might have.